face that I'm on YouTube.
The camera is not facing you.
But I get questions wrong. It's on YouTube.
Yeah. Sammy always gets the question wrong. Okay, now it's on YouTube. Yeah, okay.
It's a soap opera.
Yeah, I don't have the same. It's not Gangnam Style on YouTube, to say the least.
You get enough to get money.
No, because I did, and for 7 years I got $100, and then I understood that I should take down the ads because they're not worth it. So I just don't have ads in my videos. I have 2 accounts. In this account, I do have ads still, because in order to ask them to remove the ads, you must have 1,000 followers. I'm on 960. But on my other user, I do have it. I have like 1 million and something views altogether. But I don't. I took down the ads because the revenues are so small at these numbers that it's not worth the pain for the students.
Just
Yeah.
gambling on this side. We're
going
to talk about.
I talk about doing OnlyFans for mathematics, but I have only haters. That doesn't work the same. Yeah. Okay. On that note, we're back on linear algebra. Yeah, and span and all these things, and I think the next thing is the משפט הממדים, we call it in Hebrew. I don't think it has a general name. I'll just call it theorem. But to make sure I'm not missing anything, I'll open the wiki.
What we did last time.
What the only thing I'm bad with is understanding anything you talked about. Other than that, no. Okay. And I won't hold you accountable. I will.
You don't. My homework does.
Yeah. Yes. Okay. Yes, I did. I remember. I did because I remember you said it's 2 for 1. You said, right?
Yeah.
No, but I want 1 plus 1 gives you the third one for free. So how did you say it?
2 plus 1.
2 plus 1. Yeah. So we did the 2 plus 1, and this one is the very last thing we did. Where's the? Yeah, that's the theorem. That's the one-sided inclusion, and equality in dimension means equality. And yeah, משפט הממדים, perfect. Okay. Yeah, I know, like I said. Oh, and this I forgot. Okay.
When we talk
Great.
about that, what's the difference between the sharp arrow and the curly arrow? No, he's talking about subspace and the.
Not arrow. Yeah. This is a subspace. It's higher than just an inclusion, which is a subset. So a subset is any set of elements from the space. A subspace is a set of elements which is by itself is a space. Okay. Just I said okay many times, but I wish to make sure that I'm on track with the course. So I have today and then 3 more lessons. That's fine. That's great. Okay. That's great. Theorem. I'll start with a theorem, which I find kind of interesting. Before I write the theorem, I'll ask you, if I have one plane and a second plane. What will be the sum of these two subspaces? If I add all directions on this plane with all directions on this plane, what will we get all together? The entire three-dimensional space. Great. Now let's do dimension counting. What is the dimension of a plane? 2. The dimension of this plane? 2. But the sum of the two planes became a three-dimensional space, right? So what are we missing? In dimension-wise, I mean, 2 plus 2 is 4, not 3, right? Again, one plane is two-dimensional. Yeah, so where is this dimension hiding, in a sense? Anyone care to guess? The intersection, exactly. So that's the theorem. The theorem says that the dimension of the sum is the sum of the dimensions minus the dimension of the intersection. Exactly, that's the theorem. Okay, so it makes sense, but ones need to prove that. Yeah, exactly. 2 plus 2 is 4, minus 1, Sammy. A dot is 0. A dot is 0. Yeah, and a line is one dimension. Yeah, and a dot is 0 rather artificially because we said the span of the empty set is a dot, right? So we created it using a base containing 0 vectors, basically. But that's artificial. The fact that a line is one-dimensional, that's real because you take one vector, you multiply it by its colors, you get a line, right? Okay. So, given a vector space V finitely generated, which means it has a dimension. We talked about it, that some vector spaces could be generated only by infinite numbers of vectors, and then the whole discussion about dimension is irrelevant. And given two subspaces U and W, then the dimension of U plus W equals the dimension of U plus the dimension of W. And what is the rest of the sentence? Minus the dimension of the intersection, exactly. Okay. So proof. Let's prove this theorem. And that's one of the great theorems in linear algebra in the sense that first it looks difficult, but after you understand linear algebra, you look back at it and think, oh, this proof is trivial. And I think that it looks hard at start because it presents a new way of proving things about dimension. And before I write the proof, I wish to help you visualize the story behind it. So I'll go to GeoGebra. I won't write it down. I just need you to listen. And I'll take two planes. One of them will be z equals 0, and the other one will be x minus 2 double y plus z equals 0. And I'll paint them in different colors. Okay. So again, like I said, we're expecting, maybe I will copy it if it will come out nice to the pages. One plane is two-dimensional, meaning how many vectors do we need to create this plane? Two, right? I'll write up two vectors. So one of the vectors is 1, 2, 3. And the other one, if I'm not mistaken, will be, no, it's 0, 1, 2, I think. Yay. Okay. It could be 4, 5, 6 rather, but I don't know why I chose this one. Okay. This plane is created, spanned by these two directions. Agreed? Now, the orange plane is also created by two vectors. That would be a bit easier. 1, 0, 0. Oh, I didn't write vector. Sorry. Vector 1, 0, 0 and vector 0, 1, 0. Agreed? This is a nice base. By the way, what's the difference? Why am I saying that the base of the orange plane? Why am I saying that the set? Sorry, I'm coloring them so you can I can reference them by color. Why am I saying the two red vectors are nice? Can you guess?
They're unit vectors.
They're unit vectors, meaning that their length is 1. That's one thing. But what else? They are perpendicular. That's linear algebra 2. In linear algebra 2, you will speak about how do we measure perpendicularity and angle in general, and how do we find a base. Think about it. Could you find a base for the purple plane that contains perpendicular unit vectors? Unit vectors is easy because you can divide by its length, but choosing perpendicular lines over this generally fitted plane could be work, and that's linear algebra 2. It's not my purpose here at all, but it's one of the questions. In any case, how many vectors do we have in the drawing so far? 4. And if I take the span of these 4, I'll put it before the theorem intro. I'll put it here. And if I take these 4, they span the entire 3-dimensional space. But there's something, there is a linear dependence there. Okay? And how can I connect this story to the intersection? None of these 4 vectors are within the intersection. Do you agree? So can anyone tell me how can I solve this riddle? Because the proof will be as such. I want to take vectors for that, and a basis for that, a basis for that, a basis for this, because the number of vectors in the base is the dimension. But if I will choose the vectors as I did randomly, I'm not sure what will be the next step. That's not the way to approach it. Can anyone guess what should I do?
So we use the calculation we did to see if vectors are linearly independent, would like CA1, CA.
But I want to know exactly the dimension, not just if there is a dependence. I want to find the right vectors. That won't do. Yes, Sammy.
Doing it like
I'm not speaking about technically. I'm speaking about which vectors. No, but within this drawing, which vectors should I look at? I'm saying these vectors are not the ones to look at. How will I do it technically? You will see it's not that hard. But which vectors should I be looking at?
That's goes along the line. That's the intersection.
I'll take one vector on the intersection, and then what?
Well, that's perpendicular.
So in linear algebra 2, you write it will take perpendicular. Here I just take some other vector.
That's on the
And it's enough for the proof, because once I have one vector on the plane, if it doesn't span the entire plane, there must exist some other vector that I can choose. And that's what I will do. I'll start with a vector on the intersection, and then I will take, and let me draw it. I need to, what? Is it true? No, 2, 1, 0, I think, 2, 1, 0. So if I'll take vector 2, 1, 0, great. Okay, let's color it green. I have no green here. Fine, whatever, that's enough. Okay, if I take this vector and one of the black ones, doesn't matter which, right? Let's take the longer one. And what else? Because it's also on the orange plane. How many vectors do we have now currently on the orange plane? Do we need all three? So I can take one of the red ones, right? And now look at how beautiful. Because I'm saying the basis for the orange plane is built from these two vectors. The basis for the purple plane is built from these two vectors. And if I take all three, that's the basis for the three-dimensional space. And that's the reason that the intersection is counted twice and we can remove it. That's really the idea of the proof I'm just about to write to you. In general, the vectors of the intersection will be called V, V1 to Vk. The vectors, the so-called black ones, would be U, I, whatever, 1, 2, whatever. The vectors on the W would be W. And then I will say, if I take them all together, that's the basis for the entire thing. You'll see it in a minute, okay? But the main idea was starting from the intersection and then completing it to a base. Not completing, the word להשלים. How would I say it? להשלים לבסיס. I don't think completing is a good word. Like adding what is missing to be a base. Completing, I don't know, it sounds,
No,
I don't know.
in angles, what do you call an angle that
Complement. Complementing it to a base. Yeah, I think that's better. It's not a mathematical term anyway, but okay. So, you know, I did put the drawing, but I didn't write anything down. That was just an explanation. The theorem will be here. Okay, so take any base V1 to Vk or U cap W for the intersection. Complement it to V1 to Vk, U1 to UM, base for a base for U, not you specifically, base for you and a base for me. And okay, complement it and to a base for you. I think that's the better way to write it. And complement it also, complete or complement, whatever.
Yeah, complement is also like what everything that's not in the sense.
Yeah, add the complement. Yeah, so I'm meaning adding the complement. And the exact phrasing I think is meaningless here. So I'm also taking V1 to Vk W1 to WP. The example I showed you, the two planes were symmetrical, both two-dimensional, but the theorem is true in general, whether I'm adding a three-dimensional space to a 10-dimensional space, right? So that's why all the values here are different, okay? First of all, what is the dimension? What is the dimension of the intersection? The dimension is the number of elements in the base. How many elements are in the basis of the intersection? K. That's the number of vectors in the intersection. What is the dimension of U, K plus M? The dimension of W is K plus P. Now, if we prove that V1 to VK and U1 to UM, W1 to WP is a base for U plus W, then what would be its dimension?
What I said before, M plus P plus N.
Yeah, it would be K plus M plus P. That's the three vectors. Think of this as the green vector. I'll even add coloring to it. This is the green vector. This is the black vector, and this is the red vector. So it could be a lot of vectors. In my drawing from before, I only had 3, but in general, it could be another number. Saying these are the vectors from the intersection, this is the complement to U, and this is the complement to W. And what I'm suggesting is the union of them all is a basis for the entire sum of vector spaces U plus W. And then K plus M plus P, which is the dimension of the sum. What does it equal to? That's the dimension of the sum. That's equal to K plus M plus K plus P, right? That's the dimension of U, if I'm not mistaken, right? Yes, that's the dimension of U. That's the dimension of P. But currently, the equation I wrote is not correct, right? The left-hand side does not equal the right-hand side. If you have K, here you have K plus M plus P, and here you have K plus M plus K plus P. What correction should we do? Minus K, which is the dimension of the intersection. Okay, and that would be the proof. So all we are left to prove is that this is indeed a base for the U plus W. Yes.
Saying that the particularity is important by you who didn't do anything. The currency, I understand that it's like linear algebra too, but why is it needed?
It's not needed, it's helpful. If two vectors are perpendicular, then they obviously are independent, but it's not if and only if. Here we take independent vectors, not necessarily perpendicular, okay? And by the way, sometimes we want perpendicular, sometimes we don't. But if everything works well with perpendicularity, then things work really well. You'll see in linear algebra too. Yes.
There's okay. Okay.
Yeah, here.
This is just the principle of inclusion.
Yeah, it's reminding of inclusion and how do you say?
By principle of inclusion exclusion.
Inclusion and exclusion, but if you count the number of vectors in the vector space, it's infinity. So it's similar of, but not exactly the same. Okay? Because what is the size of the union of two sets? Is the size of this set plus the size of this set minus the size of the intersection. That's a lot like what we're saying now. But it's not exactly, because that's a whole algebraic structure with infinitely many vectors. But if we look only in the bases, it turns out to be true, right? If we choose the bases correctly. If I would have chosen, like the first drawing, two whole different sets of bases, then the intersection is empty, but it's meaningless. It's meaningless. I had to choose my bases wisely. That's the main thing. That's why I said this theorem is so pivotal here, because the idea of choosing the basis wisely makes all the difference in the world. And that happens a lot in linear algebra. Okay, so for I didn't finish the proof, but for homework, prove that, thank you. For homework, prove that the span of A union B equals the span of A plus the span of B. We do this with a two-sided inclusion. It's on the videos as well for whoever wants to see, but I don't wish to do it here. It's helpful here. Therefore, this set over here, which is the union, right sense. Therefore, just a second. Therefore, sense and this is the union of the bases for the two vector subspaces. It spans U plus W. Okay, using that theorem, I'm saying span A is U, span B is W, so the span of the union is U plus W. Okay, and why am I doing it? I wish to prove that this is a basis, right? And because it's and in order to prove that some set is a base, we need to prove that it spans everything. That's what I just said. And what else? It spans, and what the second condition for being a base? A set of vectors is a base if it spans everything and independent. There's nothing redundant there, independent. So the independence is the main idea of the proof, which I will do. Next, we need to prove this set is linearly independent, and therefore a base spans and independent. And that's all we need to finish the proof. Okay, how do we prove that something is independent?
I was saying, or that,
What?
I mean, the calculation,
What?
C1 times B1 plus
Yeah,
C2
take
0.
null combination A1, B1, AK, VK plus B1, U1, BM, UM plus C1, W1, P, WP equals 0.
Letter.
Yeah, CP. Yes. So we take a null combination. What we must prove? What do we must prove? We must prove that all of the coefficients are 0. Exactly. And the only question is how to do it. And personally, I know, so it won't be that hard. But but what I'm saying, it's not trivial. It's not trivial. So first off, I will move some things to the right-hand side. It's not clear why am I doing it. Like I said, I know the proof ahead. I didn't invent it even myself. Okay, that's one trick, but it's a great one. I moved all the W's to the right. Why does that help me?
W was from
Let's
W.
call this vector x. Okay, so this is x. It's equals to that. Both of them are x. So since x is made of w's, where does x belong? In w, due to closure. If I take vectors from the w vector space, we have closure. Their linear combination is within w. Agreed? But also, x equals to that. Where are all these vectors coming from? From U. Just U. There is no V. There's no, the V is the whole word. But V are the intersection. Yeah, the basis for U is this. It's just from U. So X is both from W and from U. What does it tell us about X? Not plus, in the intersection. So therefore, X is in the intersection. And therefore, and thus, just to be diverse, and thus, because it's in the intersection, it is a linear combination of the base for the intersection. Agreed? So now I have 3 different ways to create X from directions. I know how to create X from the U vectors. I know how to create X from the W vectors, but therefore I can create X only using the intersection base. And now, since X equals X, I can say that this equals that. And then I'm moving it back to the left-hand side, and I get D1, V1, DK, VK, plus C1, W1, plus, and we're almost done, CPWP equals 0. What do you know about V1, VK, W1, WP? But not just in W, they are the base for W, right?
Yeah.
And if they are a base, what do you know about them? Yes, for W. Okay. They are a base for W, so therefore they are independent. What does it tell us? If there is a null combination of independent vectors, yeah, and yes, since V1 to VK, W1, WP are independent, are a base and therefore independent, all of the coefficients are 0, and specifically C1 to CP are 0. We are not yet done because we needed to prove that all the coefficients here are 0. Which did we prove are 0? The C, right? But I'm going back here. And since all of these are zeros, therefore, by the first equation, we get that only this part, or you can also think of that equation because this equals 0, we get that this equals 0. But again, what are these vectors, V1, VK, U1 to UM? So, and again, these vectors form a base for U, and therefore are independent, and thus all the coefficients are 0 UD. Okay, that's the proof. The D are 0 as well, but I don't care about them. They were just means to an end. The coefficients I needed to prove are 0 were the original A, B, and C. D was means to an end. But they are indeed 0. That's true. Okay. Any questions so far? So that's like, I think it's almost the first time you actually see linear algebra. It took us some time, but that's linear algebra. That's well, that's the theoretical aspect of linear algebra. The practical one you saw. That's Gauss elimination. Okay, that's the yeah, that's the whole thing basically.
Not understanding it.
What?
What have I been not understanding until now?
Are you asking? I need to go back to the start of the course to
Just like I have been understanding not linear algebra, so I don't know what I have been not understanding.
Yeah. Okay. Yes. So now you're ready to start not understanding linear algebra. Okay. Of course, it was some kind of exaggeration, but in many sense, that's like linear algebra, the vector spaces, because we prove these things in general, not just for geometry, like I've shown you a few times, with the sound waves and whatnot. All these proofs hold for every vector space, even the interesting ones. That's why it's important that we do it in general, not just a geometrical proof for these ideas like the plane and the plane. Okay. Next, this was rather theoretical, And next, I wish to do something more practical. So next, we will study the three vector spaces that arise from a given matrix. That would be our main tool to actually calculate dimensions. Okay, so the next part will be rather technical. This was theoretical, a general proof, but you don't know how to find bases and how to find dimensions and so forth. So the next part will be as such. So we'll take the break now a bit early because that's the right spot and get back at 10 past. 10 past. See you. Okay, we're back. And like I said, next few, I don't know, things, I think even until the end of today, we will do some technical work. But short time before technical work, theoretical definitions. Given a matrix A of size m times n, we define the row space of A to be the span of the rows of A, the first row of A till the M row of A. Meaning you look at the rows of the matrix. I will give you an example in GeoGebra afterwards, but you look at the rows of the matrix as vectors, and you see what is spanned by these vectors. This is contained within, what is the size of each row? N, exactly. Okay, this is contained within Fn. Next, the column space of A is very similarly the span of the columns. First column till the n column, contained within Fm. And the last subspace we actually know, I don't remember if I referenced it by its name, the null space of the matrix. It's all of the vectors in Fn such that Ax equals 0. So the null space of A, we are very familiar with. We know how to solve it. It's the Gauss elimination and finding the general solution using the free variables. The row space and column space are new. In any case, I will give you a few examples that shows all of them, but NA is supposed to study them until now. Agreed? Note, we can find bases and dimensions for all three subspaces of the matrix. It's not that the matrix is the space. I'm meaning subspaces, I don't know, that arise from the matrix, like I said before. I think in Hebrew we also said מרחבי המטריצה. We also say it. I think sometimes it confuses the students. The matrix itself is not a vector space. It's just, I don't know, a set of numbers. But arising from that are three important vector spaces. So we can find all of the bases in the dimension using one Gauss elimination process. Okay, so that's kind of like the point, the end of the thing, but we will see how to do it. But given a matrix, we do Gauss elimination once, and we have the dimension and basis for the row space, a dimension and basis for the column space, and a dimension and basis for the null space. Okay, and I will show you this using examples. Example. Consider the matrix. Matrix. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? First, the row space is the span of the vectors in the rows of the matrix, i.e., what is the first vector of the I'm speaking about? 1, 2, 3. The second, 4, 5, 6, and the third is 7, 8, 9. Okay, so these are three vectors in R3, and they form some space. I think we've seen a lot of times this specific example. Can anyone remember what is the dimension of the space? It's 2. It's a plane, right? Okay. I'll draw it up in GeoGebra before I'll show you how to actually calculate things using the Gaussian elimination. It's the same time of the day. Well, so confusing. Clear all, start from the start. Vector 1, 2, 3, vector 4, 5, 6, vector 7, 8, 9. Okay, we have the three vectors here, and they do form they span a plane, but we don't need to use GeoGebra to solve it. We will do Gauss elimination, but I wish for it to be visualized in your eyes to understand that we're actually calculating something using the matrix. So these are these three vectors. These are the rows. So the span is the row space. The column span, the column space is the span of, yes, of the vectors in the columns. 1, 4, 7, 2, 5, 8, 3, 6, 9. Agreed? Before I draw it, does anyone have a guess whether there is some connection between the row space and the column space? Why?
Because I remember you said it.
Very helpful, Thomas. Yeah. So it is true that the row span and the column span have the same dimension in general. Are they the same space in general? And in this case? So in general, no. In this case, we can't tell, right? Because you see three different vectors. But one of the things you must realize by now, the different vectors could lie in the same space, right? So we don't know. If the matrix was not, if it was rectangular, not square, then it's obviously could not be the same space because it's in different worlds altogether. But when the matrix is square, both spaces lie within the same world, and also the null space. They are all within the same world, but the connection between them is not necessarily special. There are some connections, some of them you'll learn in the future, but the main one here will be that the dimensions of them has to do with one another. You will see why. So next, I will draw up these three vectors. I'll disorient you, so you won't see the connection to the other vectors yet. Vector 1, 4, 7, vector 2, 5, 8, vector 3, 6, 9. So first of all, you see, yes, they form a two-dimensional space. Okay, they form a plane. Okay, let's copy them also onto the file. Wait. Well, weird. Okay. And lastly, the null space, in order to calculate the null space, we must solve the homogeneous equation AX equals 0. And I have no other way to put it. And in order to solve it, I need to do Gauss elimination. So I'll do it. Okay. And the matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'll do R2 minus 4 times R1, R3 minus 7 times R1. And we get here 0, minus 3, minus 6. I'm not calculating it, I remember it. That's minus 6, and that's minus 12. Next, we will do R3 minus 2 times R2. And we get the third line becomes 0. This is echelon form, but not reduced. I want the reduced echelon form because I want to find the solutions to the homogeneous system of equations. So I continue. I divide the second row by minus 3 to get the 0, 1, 2 I wrote before, by the way. 0, 1, 2. And lastly, what is the last operation here? R1 minus 2 times R2, which gives us 0 and minus 1. So we plug into Z equals T. Therefore, Y equals minus 2 times T. And X equals T as well. So the null space of the matrix are all of the vectors of the type T times 1 minus 2, 1. Which is the span of 1 minus 2, 1. What is the dimension of this space?
1.
1. 1, because it's one direction. right? Just thought of the Backstreet Boys. Okay. Any questions so far? One Direction? What's the difference? Is there?
Or the other.
Yeah. You know what is funny? I tried to think of a song, and then it went in my head, baby, I did it again. That's not either of them, right? What Backstreet Boys I should know, it was in my time. Not Hit Me Baby One More Time. What the Backstreet always had?
What's
They have a song, I know it.
our back or something? That's like
I'm back. Hit me one more. Okay. And One Direction, what do they have?
songs for teenage girls.
Yeah, but for example, which song for teenage girls? Okay, sorry.
That's
Yes. Some song.
everybody. That's a good one.
Everybody.
The song is good. The best song.
Oh, really? That's its name. That's like, what's your name on the paper? My name is a passing student. By definition, I must get a passing grade. Okay. Yes. Okay. My name is Bobby Drop Tables. Do you know that XKCD? Okay.
But who calls you their child? Bobby drop tables. You can.
Leo Bobby underscore
Yeah.
semicolon underscore drop table.
It's SQL injection drop. I'm sorry.
Yeah, yeah. I can explain it later. In any case, it's one-dimensional. And can anyone care to guess where on the GeoGebra it will appear? I mean, geometrically, right?
Yeah.
It's on the space, that's true, but okay. So,
It's that line.
I'll-
Intersecting the different line.
no. I'll put it on GeoGebra. First of all, I'll delete these vectors and I'll disorient you. And then finally I will write them all together and we'll see the different connections. Some of them are always there and some of them are special to that specific matrix. What? Yes. Yes. Yeah. Yes. That still for the life of me can't understand why this can get the Wi-Fi on the university. Thank you. This can get the Wi-Fi at the university and give a hotspot to that computer. I'm not using the cellular. This doesn't use the Wi-Fi well. The phone does. It probably has something to do with vaccine and 5G, but I'm not sure.
The 5G is turning the frogs gay.
No, I'm always saying that I'm so annoyed because I got all the vaccine and I still don't have good reception. I was lied to. Okay.
Please communicate.
Yes, yes. Okay. So now, in all seriousness, So in general, the row space and the column space must have the same dimension, but they don't have to be equal. In that specific matrix, they are equal. So all 6 vectors are on the same plane. The null space, what it is? The null space is perpendicular to them. And what is generally true is that the null space is perpendicular to the row space. That's linear algebra 2. You don't have to know it, but that's always true.
It's scary when you say generally, because it means that there's probably like 50 cases where it isn't. And
No other way around. When I say it's generally true, I mean it's always true. That's what I meant, not in this specific example. By the way, for a final thing that I will say about it, in the real numbers, in the complex numbers, it doesn't work that way. In the real numbers, the null space is perpendicular to the row space in the real numbers. But again, that's linear algebra 2, and doesn't matter for us now. It's also look like Games of Thrones, right? Yeah.
The Iron Throne.
Yes, exactly. The vector throne. Yeah. The throne.
Like with all the swords and whatever.
That's the throne with all the. I didn't even watch the show and I know it.
Null space. So good.
Yeah, that's what that's the seat. That's the seat. You're sitting here, and that's
Just to manipulate vector space a bit, so it's
yes. Now I'm writing it out. That's the vector throne. Okay. That's not for the test. Yes. Okay. Yeah. What is that? Yes. The funny thing is that you would prefer it to be the test, right? Yes. Yeah. Okay. Now how do we find the bases and of CA, RA, and A? So I'll write the bottom line. We perform Gauss elimination, and obviously, one.
Yeah, we should take a shot every time.
The rows, bullet shot. The rows different than 0, not 0 rows, obviously, are the base to RA. The rows different than 0 in the echelon form. Okay. 2. So one possibility is to transpose, then the columns are the rows, and do it again. But I promised you one Gauss elimination, so you don't have to do it. The columns from the original matrix of the bounded variables form a base for the column space. So what I emphasize is really important. When I take the basis for the row space, I look at the matrix after the elimination. When I take the vectors for the column space, I take the original vectors, the original columns from the matrix. It's very important because the Gauss elimination destroys the columns. It makes everything zero at the end. It's not the original space, but we still know where do the base vectors lie. And 3, the direction vectors from the general solution to the homogeneous equation form the basis for NA. So now let's talk dimensions. What is the dimension of the row space? It's the number of rows different than 0. Agreed? Note, the dimension of RA is the number of rows different than 0. Yeah. In the echelon form. Okay. What does it also equal to?
Okay.
But why?
The amount of bounded variable.
Exactly. That is equal to the number of bounded of, I'll say it in 2 steps, of pivot elements, right? Because every row different than 0 has a pivot element starting it, and therefore the number of bounded variables, which is the dimension of CA, right? Because we said that the basis of CA are the columns of bounded variables. So that's the reason that and I didn't prove it. I won't prove this theorem. It's on the videos whoever wants to watch. But that's the reason that the dimension of the row space and the column space is always equal, because it equals to the number of bounded variables, the number of rows different than 0. And this number altogether, definition, the rank of A, the rank of a matrix, is the dimension of the row space, which is also the dimension of the column space, which is also the number of bounded variables. Agree? It's called the rank of the matrix. Yes. Yeah, because that's the way to calculate everything. If you want, we talked before, like, I don't know, the theorem about the dimension of the sum and the intersection, how to calculate all of these. You do it using matrices. You put the vectors in either columns or rows, and then you find the row span and the column span. That's like the technical way to solve the problems. I will show you a few examples later on. And what else? Also, another note, the dimension of the null space, how many vectors do we get here? Like in this case, we got 1 vector. Why did we get 1 vector? Can anyone guess or know?
Because we only have one free variable.
Exactly. The dimension of the null space, the number of vectors in the basis of the null space, is exactly the number of the free variables. It's not rank, is the number of free variables that was the bounded variables, the rank, and these are the free. Therefore, if I take the rank of the matrix plus the dimension of the null space, so that's the amount of bounded variables. That's the amount of, I'll write it. That's the bounded variables. Bounded variables. That's the free variables. And if I sum them up together, what do I get? The number of variables. What is the number of variables? The number of columns. Rows are the equations, columns are the variables. So it's, in this case, what did I say the size of the matrix is? I don't have a, that's a programming answer. No, but that's not true. It's not that, it's not true.
Oh, yeah,
It's
no.
not true, it's not true. So I'll just write n, but I write, what does n mean? It's the number of columns. I'll just write columns. So that's another theorem. We will probably prove it later on in a linear transformation language. For now, I am content with the reasoning I gave you using the three spaces of matrix. Any questions thus far? Yes, Sami.
Wait, listen.
Now or?
I didn't really. Okay, yeah, walk through this.
Yeah, when I say direction vectors, I'm referring to a high school concept. Here, I found a general solution t minus 2t, and I took t out, and I called this the direction vector. Okay, and if I had a few free variables, then I would have a few vectors here. I will do another example in a bit. Any questions? Okay. Let's do another example.
Sorry, rank is also the amount of independent vectors, right? I thought that's
What does it mean, amount of independent vectors? It's the base. It's exactly that, right? It's the same thing. Yes. Okay. So example, I'm trying to think of how to formulate it. Let's do another matrix, and then I will show you examples when the question is not about the matrix. The question does. Let's do it now. No, it's important for me for you to see it. Okay. Find the dimension of U, which is the span of 1, 2, 3. I will give different numbers now. -2, -4, -6, 1, 1, 0, and 0, 1, 3. Okay, so these are 4 vectors in the 3-dimensional space. The dimension is obviously not more than 3 because we're in the 3-dimensional space. There is obviously a linear dependence here because you can never have more linear dependent vectors than the dimension, but still it could be either 1, 2, or 3. Okay, and I want to find the dimension. So this question has nothing to do, allegedly, with a matrix. You must be the ones to say the main tool I have to answer this question is use a matrix. So I take the vectors and I create a matrix for them. And then one of the most common asked question by the students is whether should I put them in rows or in columns. And the correct answer is columns. No, I'm half kidding. I will almost always show you how to put them in columns to make it helps to have order in your head. But the TA may show you something else, GPT may show you something else, every other source, because everyone has their algorithm that they like. The main thing is for you to know that if you put it in columns, you are looking at the column space. If you put it in rows, you're looking at the row space. That's the most important thing to do. Put it as well as you like, but you need to remember how you put it and what you're studying. That's all. Okay. So we'll put it here in columns. And one of the reasons, there are many reasons, but one of the reasons I like columns is they keep the original vectors as is. In the row space, the algorithm says do Gauss elimination and take the rows of the new matrix. They are different than the original ones. When I put them in columns, I take from these the few vectors which are independent and they form a basis. So it has to do with the question. If the question was, choose a subset of this set of vectors which form a base, you would be forced to do in columns. Okay? And I can't think of any question, almost any question that would have forced you to put it in rows, but I don't know. Okay, in any case, we will put these vectors in the columns of a matrix and study the column space of that matrix. That's the way we're going to solve it. So the matrix is 1, 2, 3 minus 2 minus 4 minus 6 1 1 0 0 1 3. And that specific, I wish to note it. RA and NA are meaningless here. Because I put the vectors in the columns. The column space is all I need in this specific question. Okay? Okay, so we do a Gauss elimination. Surprise, surprise. I won't bother to write. I will bother. R2 minus 2 times R1. R3 minus 3 times R1. And we get 2 minus 0. This is 0. 1 minus 2 minus 1, 1. Here, 3 minus 3, 0. Minus 6 minus minus 6, 0. 0 minus 3, that's minus 3. 3. And lastly, was kind of fast, R3 minus 3 times R2, which gives us 0 and 0. Agreed? So now what should we do? we mark the pivot elements, this one and this one. Therefore, what are the bounded variables? Why? Z, but the first and the third, I don't care about the names, right? The first column and the third column, right? The second column is that of a free variable. The fourth column is that of a free variable. So what did the algorithm told me to do? I take the columns, the first and the third, from which matrix? The original one. Thus, the column space of A is the span of the first vector and the third vector. That is the basis. And what is the dimension of this space? 2. It's a plane as well. Okay, it looked like 4 vectors, but 2 of them were linearly dependent in the other 2. Yes, Thomas.
I'm glad I'm starting to not understand linear algebra.
Yeah.
I
No, but this is not linear algebra. This is cheshbon, right? This is not algebra. So I'm kidding, but like, in a sense, I'm not kidding. Like the operation addition and multiplication are arithmetics, cheshbon in Hebrew. They're not like the mathematics, right? The mathematics is the algebra. So the Gauss elimination, the matrices are like the arithmetics or linear algebra, and the vectors are the purpose, right? But yeah.
I just don't understand, like, you put the vectors in columns, and when you perform the Gauss elimination, you're
Destroying the columns.
destroying the rows. Like you're affecting vectors. by
Yeah, it's
themselves.
weird that it works. It's weird that it works. I can, because I skipped the proof. I urge you to watch the video about it. Okay, whoever want to go dive a little bit forward. I think most lectures don't show the proof anyway. I do because I don't like skipping proofs, but in this case, because we need to, like I always said, it's less art than mathematics. I need to take out some things. This won't be important more than your sense of okay, I'm fine with
Yeah,
it, right?
I just don't.
It's surprising that it's work, but it's not that surprising. The putting it in columns, meaning you're solving the null combination. What we're solving here is actually the null combination, and the free variables are of these vectors that you can create using the others. That's really on the tip of the tongue. Tip of the tongue, no. Tip of the iceberg. In Hebrew, it's tip of the fork. קצה המזלג. Yeah, tip of the iceberg, I think.
Sure. So going back 1 second to the definitions, you said that you get CA by seeing the independent variables, the bounded variables.
Yes.
But it's not the bounded variables of the row form, it's only on the column form.
The location of the variables are columns, right? It does make sense in that sense, right? You find the pivot elements are by rows, but once you have a pivot element, it affects the column. Say this column represents a bounded variable, right?
Yeah, what I mean is that if you would have put the matrix on the row form instead of...
Then I would do the algorithm for rows. It's something else completely. Let's do it for a second, just for the sake of the game. Let's solve the same question using rows. So the matrix, let's call it B this time. It's actually A transpose. Let's call it A transpose. The matrix A transpose is matrix is 1, 2, 3, -2, -4, -6, 1, 1, 0, and 0, 1, 3. Okay. I put the vectors in rows, and now I will follow the algorithm. Now, CA and A are irrelevant. Okay? And what do? I do Gauss elimination and take the rows different than 0. Question, how many rows of zeros will we get here? 2, because we know that the dimension is 2, so we must have exactly 2 rows different than 0. Okay, and you will see that actually happens. So let's eliminate this matrix.
And that's what you're doing.
I don't care about the column space of this matrix. It says nothing to me that has to do with the question, right? The question, the original question, Sammy, was about these 4 vectors. These are the rows of this matrix. What do I care about the columns of this matrix? They are meaningless in this question, right? Because when children, when students, when students ask about, think about or presented with the spaces of the matrix, they see a matrix, they expect always all the spaces to mean something. They don't have to. I didn't start with the matrix. I start with vectors. I put them in rows. The rows of the matrix are important to me. The columns are incidental, right? Okay. And you are children to me, but because I'm old. Okay, so R2 plus 2 times R1, R3 minus R1. And that's it, because the last element here is already 0. I don't have to do anything with it. Here we get 0, 0, 0. Here we get 0, -1, -3. How do you say marabout in English? Do you know marabout? One of you know.
Malibu, the place.
That's true, but not Malibu. Marabout. It's true that it's a bird, a rather ugly version of a stork, but I'm not speaking about it. If you didn't know, then I will educate you. Marabout, Masecha Hashem. So it's like OMG of the religious guys here. So they say for short Marabout, and the teenage girls say Si a Marabout. That's like literally OMG. Like, okay, whatever. So how beautiful. Yeah, that's what I was amazed by. Every day you learn something new. It's not always truth, but it's new.
The things to learn in linear.
Yes, yes. No, in Bar-Ilan, that's Bar-Ilan. Okay, R3, I don't know, plus R4. Yeah. Yes. Okay, so 0, 0. And lastly, I really won't bother writing the operations I'm making, but I change the order. And this is 1, and this is 3. This is 0, this is 0, meaning that the row space of this matrix, it's actually A transpose, to be honest. The row space is the span of the rows different than 0. 1, 2, 3, and 0, 1, 3. So we found two different bases for the same space. On the one hand, this one, that's the second one. And on the other hand, who remembers it was 1, 2, 3, and what I'm saying is, and I'll draw it up in GeoGebra in a bit, that these are actually two different bases for the same plane. It's a plane, it's a two-dimensional plane, and these are two different bases. One of the vectors is the same, the other one is different, and you'll see it in a bit. Okay, both solutions are completely valid. It's important to know what you're doing, not just remembering that it has something to do with a matrix and its echelon form. You do need to understand a bit more than that to actually solve the problem in the test. Let's look at GeoGebra. They are all, I'll put the vectors here. The first vector was 1, 2, 3. The second vector was -2, -4, -6. What is the connection between these two? They are on the same line, on the two direction. The linear dependency here is through the roof. And next, it was 1, 1, 0, right? Vector 1, 1, 0. That's on another direction. No, no, no. And the last vector was what?
0, 1.
No. Yes, you're right, 0, 1, 3. Okay. So these are the four vectors. Think from this angle, you can see they are actually all in the same plane, right? And what we found out is, first of all, if I take only the first and the third, that creates the plane. I don't need anything else. But we also found out that the first and the new vector, what was it? 0, 1, 3. Oh, wow, it's one of the vectors. That's incidental. That's incidental. After I did Gauss elimination, is it incidental though? Oh, it's not. It is incidental in general. We didn't touch that row. We nullified the two center rows, but it's not incidental. It's incidental in general. I mean, usually when we do a Gauss elimination, we won't have the original rows of the matrix, but in this case, that's exactly what happened. Okay, fine. So it's either these two or these two that form the base for the plane. Any questions so far? Yes, Thomas.
So these results are equivalent.
These are two different bases for the same plane. Yes. And makes sense. Okay. Another example. Now let's do a rectangular matrix, not a square one. And I'll start with the matrix this case. So the matrix will be oops, that's not what I want at all. The matrix will be 2 by 3. Yeah, I think that's nice. 1, 1, 2, 2, 1, 1. That's nice. I'm allowing myself to invent number on the spot because, like I say, it's like arithmetic. There's no way to go wrong about it. I will get some answer. Maybe the numbers will be not nice, as students would say, but I will definitely get an answer. This matrix has a row span, a column span, and a null space. So find bases and dimensions for row span of A, column span of A, null span of A. Agreed? So what do we do? Echelon form. Yes, here it goes. Okay. Now I really won't write the operations I'm doing. Second row is minus 2 times the first row, so that's 0, that's minus 1, that's minus 3. And then, first of all, it's 1, 2, 3. And yes, and first row minus the second row, 0, minus 1. It looks the same as the other one, but if it is, that would be so annoying because I tried to invent new numbers. You might suspect by the end of the lesson there is only one plane in the world. 1, 2, 3 is really surprising, but I think the 1, 0, 1 is. I think it's from a previous example, not the last. No, it's with 1, 2, 3. Wait, 1, 2, 3. No, it's not the same. 1, 2, 3 is here, but it's not there. Whatever. I think it's not. So what would be the row space? The row space is the span of these two rows, 1, 0, minus 1, 0, 1, 3. That's the row space. What about the column space? No. You take the pivot elements. Yes, exactly. You take the pivot elements and you take the columns from the original matrix. So it will be 1, 2, and 1, 1. Because it's two-dimensional space, it's all of the plane, right? Because we're in a two-dimensional space. We found 2 by the 2 for 1. No, 1 plus
2 plus 1.
2 plus 1. No, it's not 2 plus 1.
You need 2, you get 1 free.
Oh, yes. Oh, so confusing for me. Yes.
That's
No, because for us, we're focusing on the third. You still say that the third is the 1, the 2 plus 1. Okay, whatever. In any case, that by the 2 plus 1, if we have 2 vectors, that's the number of the dimension, and they are independent, then they must span the entire space. Okay? Here, it's also two-dimensional, but it's not the entirety of our cube. Okay? And the null space. How do we find the null space?
Because we have 1 free variable, we need to make
Yeah.
z equals t.
Z equals t, exactly. Y is minus 3t. X is t. Therefore, the null space is all of the vectors t minus 3t t, such that t is a real number, which is the span of 1 minus 3, 1. Agreed? And I'll it's one-dimensional, okay, and 1 plus 2 is 3, and I want to put that in GeoGebra. Clear all. And so, first of all, the vectors of the plane, which are what? No, the plane in the three-dimensional space, the row span. It's 1, 0, -1, then 0, 1, 3, vector, and 0, 1, 3. And the last, and now I'll put the vector from the null space, which is 1, -3, 1. Vector 1, -3, 1. Where does it appear to be? Perpendicular to the space. These two are not perpendicular to one another, but the null space is always perpendicular in the real numbers to the row space. Okay, so that is what we get here. It's hard to see it like that. So I'll write the plane. X minus 3y plus c equals 0. And I think now it will be clearer to see that the two vectors are on this space, and the null space is perpendicular to it.
You're wrong. The plane that is the null vector and one vector.
Are you asking why? How did I know it was x minus 3y plus z?
No, I think I understand why. I'm just mean, I thought you were going for the plane from the two vectors, nothing.
It is the plane from the two vectors. Don't you see?
No, I mean the plane from the two vectors that are in the null space.
Yes, that's exactly what I did. The two vectors that are in the null space are these. And I took the plane that goes through them.
I thought the small one was the null space vector.
I'm telling you, I'm trying to, I understand your confusion. I'm trying to solve it. And the reason I did this, because in my head I was untying the knot. But so solving it, and then comes out violent. Exactly. Let's solve it. Okay. So first of all, do you agree these two vectors are from the row space of the matrix?
Yes.
If you don't, then just look for a second. This is 1 minus 3, 1. Okay. So these are the two vectors from the row space, and this is the plane that goes through them. Agreed? Now, what did Thomas see that confused him? He saw that I wrote the equation for the plane, and the coefficients here are from the null space. The reason is, and it's because the null space is perpendicular to the plane, and the coefficients here are the normal vector to the plane. So it's not a coincidence that there is a connection, because the plane is the null space of this equation, and its rows are this. So in simple words, the perpendicular to the perpendicular is me.
Okay.
I am my brother's brother. Okay, that's what happens here. It's confusing. It's more linear too, but I think they don't even actually get to teach that. But that's what's happening here. Yes, Sammy.
If we wanted to code Gauss elimination, would it be recursive?
Yes. And if we wanted to prove that there exists Gauss elimination, and if we wanted to that it always ends up with an echelon form, and if we wanted to prove that a reduced echelon form is unique, we do it using induction, where the idea is exactly recursion. We assume we take out one column and say, okay, we have a matrix, we can do a Gauss elimination, and then take add and bring back the last column, see what happened to it, and then finish the job, right? So yes, It's really recursive in nature. How actually computers do it, it doesn't have to be because of יעילות, runtime. You want low runtime, and there is a lot of work about how to do it as fast as you can, and also keep the errors to a minimum. Because when you actually do it with a matrix, with numbers, and numbers, float numbers, has some error always. It's not the perfect number. And when you do a lot of operations, you increase, thank you. You increase the errors. So there is a lot of work. I'm not specifically knowledgeable about it, but there is a lot of work in this area of expertise. Yeah.
If we want the the basis, then what we have to do is
Put it in column and then show that every column have a pivot element. That's all. That's all. That's why I said that what we learned today is the most technical part. That's the way you answer most questions. Okay? Any questions so far?
I don't think, without doing exercises, I'm not that for the start. I can ask you a question.
But these are the exercises.
I know, but like, it seems like something that comes with repetition. Because
Yeah, no, that's obviously, that's true. That's true. Only once you do it a few times, you're able to succeed. So I'll mention you once again, what should you do in order to study for the exam? And I urge you to study for the exam now rather than later. I'll just open a test, quick test. So, yeah, no. The problem with this question, they are all involving other material as well. For instance, this is like you had on the quiz. You eliminate with parameter, but because it has to do with the linear transformation, I cannot tell you should solve it. Okay, I know how to solve the problem. I knew before, and this is also yeah, it's all linear transformation. Okay. עמוד ראשי, באר שבע, semester ב', linear algebra. Okay, these are the tests in linear algebra for teachers. It's easier, okay? And I think that's good. Okay. Look at the following tests. Link. I think I linked for this very page sometime during the semester. For instance, let's look at this one. The first question is actually a question for 5 Yachal on the matriculating test in complex numbers. You should be able to solve such question, but it's not super relevant, to be honest. The second question is just as you had on the quiz. You should be extremely fluent in it. That's your ticket, one of the tickets to passing the exam, because there will be such a question on the exam. You wish to get all the points you can get from it. Okay, it will be, I don't know, 20 points, maybe even 25. That's a lot. The third question is what we learned today. I still did not teach you how to calculate the basis for the intersection, I will do that. But find base and dimension for the three spaces of the matrix we learned. Actually, now I'm noticing it is the very matrix we just did. Okay, it's not the same on all tests. It's funny that it's on the test, yeah. Right, okay. I use it a lot. Yeah, I use it a lot. Yeah. But yeah. So
We provide that specific
I think we did it
matrix.
because-
no, this is different. No, this is different. This is different. You have 1 and 3, but okay, these are all numbers. Don't. It's not the same order even. Okay, yeah. So it's kind of the same. So solve question number 2, and you can do. Okay, I'll write. Solve questions 2 and 3, and try 4. No, one you should be able to, but it's not because it was for teachers. We're going to teach 5 yechidot limud. I put them in calculus. I did the same. I took questions from the matriculation test and put it on their test, because they will say, "Oh, what you teach is so philosophical. It has nothing to do with the bagrut." So I got annoying with it. And sometimes say, "Okay, this is a question for the bagrut. You can't say it's not relevant anymore." And then they say, "Oh, we choose the other subjects." Okay. Yes. Okay. So yeah. Any questions so far? So notes. I did not teach you yet how to find the base for intersection. It's funny because most lecturers believe that you're somehow supposed to be able to solve it by yourself. And you are able to solve it by yourself, but not teaching it is stupid. And one of the reasons is because students, when they don't have an ordered process, each question they do something a bit different, but there is actually a very ordered algorithm as to how to find the intersection. I will show it to you. But if you get I don't know, confused using intersection, you're in a good company. Most students do. Okay. Next. It will be a note. We have learned 2 ways to present a subspace. The geometric approach, which is the span of direction vectors. Saying these are direction vector, what can you create from them? That's I call the geometric approach. And the algebraic approach, which is the null space of a matrix, the solution to a set of linear equations. That's the algebraic approach. From which approach will it be easier to find the intersection? Let's look at it. Because we had it before. We saw here this. No, not this. Yes, this. Yes, this, but I didn't write the, okay. I didn't write the numbers. For instance, say you have the span of 1, 2, 3, 4, 5, 6. And you have the span of 1, 0, 0, 0, 1, 0. Is it easy for you to find the intersection from this approach? No. That is not good. However, if I will tell you Gauss elimination, if I will tell you find the intersection of all the x, y, z such that x minus 2y plus z equals 0, and all the x, y, z such that z equals 0. Would it be easier to do it in the algebraic form? Yeah, that's exactly my point. You have two different ways to present the same space. That's the geometrical presentation, and that's the algebraic representation, right? But using the algebraic representation, it's much easier for me to find the intersection because it's actually all of the x, y, z's such that both equations hold. X minus 2y plus z equals 0, z equals 0. And now I can put it in a matrix and solve. Right, that's the null space of 1 minus 2, 1, and 0, 0, 1, which is the null space of here 0, and then we get y equals t, x equals 2t, and not surprisingly, z equals 0. So the null space, the intersection is t 2t 0 such that t is a real number, which is the span of 1, 2, 0. And if you remember, that's exactly the vector we chose when we presented in the GeoGebra, but there you used guesswork in a sense. But this is a process. And all that you're missing from being able to do it by yourself is to know how to do the converting process from the geometric representation to the algebraic representation. I will go over it next lesson, and then we start linear transformation. So we're good on time. Yes, Sammy.
Could you just plug the Z and say, okay, the Z always has to be 0.
Yeah, it's silly. It's a silly question, Sammy. We talked about it when we started linear equation. And then I told you if you solve it using substitution, you may miss some things. That's why we do it always in a matrix. And obviously, like when computers do it with 1,000 by 1,000 matrices or more, you rather do it using a matrix. Yeah. No, it's okay. You shouldn't be ashamed of being so simple-minded. No, but it's not a simple-minded. It's annoying. I tell you why. It's the advert to change, right? You say, this is a new way, but I have my old ways. Should I really learn something new? I'd rather do whatever I did up until now. Okay, but again, you're not the only one. You're just the one speaking up.
Yeah, I
Okay.
honestly, it's like me, I just don't know what I was gonna.
By the end of the course, I hope you will know what you don't know. Okay, enough for today. Have a nice day and see most of you in half an hour.
It's like that professor for quantum mechanics. It's like, this is a beautiful day because right now I'm the only one that doesn't understand quantum mechanics, but by the end of the course, all of you will also not understand quantum mechanics.
Yes. Yeah, no, but I do understand that. So that's not quantum. Actually, quantum mechanics is linear algebra, but linear algebra is not quantum mechanics.
It might as well be up right now for me. So
Yeah, no, you're exaggerating, Thomas.
no, it's not that bad. Just like so many things that we can't just give the explanation for some reason or another.
I don't, but it honestly wouldn't have helped you at all.
I mean,
The things I skipped would not have